Integrated treatment is a complex subject. The complexity of this is dictated by a variety of impacts. It's dictated by the chemistry, the microbiology, the engineering, the physics, the hydrogeology, and general real-world cussedness as well. This approach of joining treatment technologies together has formed the principal topic for 2010 series of seminars that Regenesis has been giving. These are morning seminars. They provide about 4 hours of CPD, and they're in venues around the country, or in some cases in clients' offices when there are enough people around. This particular talk, the next one is tomorrow, by the way, in one of the seminar theatres outside. This talk attempts something of a 15-minute summary of a morning seminar. So rather than write very small and talk very quickly, what I'm going to do is try and attempt some of these topics as a bit of a question and answer that I'll be asking myself as we go. So let me start by asking what I actually mean by integrated treatment. Well, simply stated, it's remediation technologies which are being used in combination. This might be spatially, different technologies being used in different parts of the same site, or it might be temporally, different remediation technologies used in sequence, one after another, or it may be both, where combinations of time and space are combined. Why integrated treatment? What's the benefit of this? Well, very simply stated, there are 4 main benefits. One of them is price. The other is it's possible to get better performance. Things can be undertaken in a shorter time scale, and you can get greater flexibility of results through this use. Why don't we just pick one remediation technology for a site and run with that? Well, the reason for that is each technology will have its strengths and its weaknesses. And the whole key to the integration approach is that combining the strengths to overcome the weaknesses and combining the technologies will basically overcome the weak points of one technology with the strong points of another. Hence the benefits of price, time, flexibility, etc. Isn't this just an engineer's playground? Well, I think the answer to that would be yes, if you mean that engineers remain actively and creatively involved through all stages of the program. But if this provides an ability to hit targets faster, more cheaply and more reliably, then isn't that a good thing? Basically you're putting more design into this and using less energy or less hydrocarbons, which is better than, say, an extended exercise of dead horse flogging, which we sometimes see on sites where kit remains in residence for long periods of time. So that really takes us to where integrated design came from, and why it's getting used now and talked about more and more these days. In fact, a case study from QDS would be an example of that, but I'll touch on that with a couple of other comments later on. Well, the reason that it took us a while to get to integration rather than start from it to begin with is that we really began with landfill. Before there was any remediation, before landfill there was no remediation. When people first started to clean up sites, landfill was pretty much the technique. So way back in the early days, landfill was the approach that we were using for site cleanup. Its upside was that it was robust, it's easy to prescribe and understand, and that was about it. The downside was that you might have risk of overdig when more contamination was found. Costs have become increasingly prohibitive. Complexity has increased in terms of actually finding places to dispose of the landfill material. And more importantly for some than others, the sustainability ranking of landfill is relatively low, although it depends on the project very much. With water, it was a different score. Pump and treat, when groundwater first started to be considered pretty much in the 1980s, was the one-size-fits-all technology. Its upside was that you had immediate hydraulic containment, you could have quick mass reductions, and again it was quite easy to prescribe and to understand. The downside was that you generally get diminishing returns from the applications, and you would frequently get rebound should you turn your pumps and pipes off after a period of time. This leads to effectively a pump forever trap on many sites. So alternatives to these technologies started to appear. We're now talking about the mid to late 1980s, 1988 sort of to 93 timescale. For soil, through the end of the 80s, ex situ bioremediation started to pick up, soil washing started to appear, thermal desorption, solidification and stabilisation all started to rear their heads and would get described as alternatives to landfill. For groundwater, in situ bioremediation started to appear. Air sparge, soil vapour extraction, dual phase vapour extraction, in situ chemical oxidation all started to appear. But interestingly, each of these tended to maintain the one-size-fits-all mindset. One technology would generally be used over another. So when a report will be written, there might be a technology appraisal at the end, and there might be a matrix of different technologies that might be fitted. And these would compare cost, time, efficacy, clean-up targets, all sorts. Generally speaking, there'd be a selection, and the client or the consultant would say, we're going to use that technology, and just one would be chosen. This I consider to be really the momentum of the one-size-fits-all approach that's being used. The outcome is that very often there was a bit of a gamble as to the end point that would get reached by that remediation technology. With landfill, you knew where you were going to get to. You were going to dig it out and it was going to be gone. But for some of the in-situ technologies, or ex-situ bios or thermals, for example, it was harder to be sure exactly where things were going to go. So this led, especially at the beginning of the 1990s, to a lot of frustration as new technologies were getting used and they weren't reaching the clean-up targets. The concentrations were dropping down, but the targets weren't necessarily met. Groundwater kit would become resident for long periods of time. I know bits of kit that have been in the ground for 20 years and are still pumping. And on occasions it would require endpoint uncertainties or re-evaluations. So the early integration that came forward pretty much became trying something else, integration by default. On other sites, earlier stages of integration would be to landfill the worst, bioremediate the rest. The QDS and ERM case study is a fine example of that. In other cases, for example, a number of filling stations, then a source removal or a tank pull might be followed by monitored natural attenuation. And from about 1993, ORC, the product that my company puts out, started to enter into the scene and would get used as part of backfill applications in filling station activities. It would be used to close off pump and treat systems, or in some cases it would be used as a standalone technology or to boost monitored natural attenuation. These days, systematic integration design is pretty much the norm. Spatial integrations are common. One technology is used in the high concentration zones, another in the lower concentration zones. Likewise, temporal integrations are common, where one technology might be used for bulk removal, for example, surfactant flushing to remove a lot of the gross contamination in the case study we saw just now, followed by enhanced bioremediation to get rid of the residues. And then increasingly sophisticated design and product development has followed, and this is where Genesis as a company has tended to focus, which I'll get onto in a little bit. Before I do that, are there any broad patterns to integrated treatment? Well, yes there are. And basically these are concentration patterns and matrix-related patterns. To do with the concentration patterns, these tend to exist because some technologies are more cost-effective at higher concentrations, excavation, pump and treat, for example. Some are more cost-effective at lower concentrations, enhanced bio, for example. And logically, you can see how both sequential and spatial remediation integration can be beneficial because of these two factors. Concentration patterns in broad schemes. Physical systems tend to be the ones that would be of default when concentrations are higher. If you can dig it out or pump it out, then do that. Chemical oxidation tends to fit in the middle ground. It wouldn't necessarily be the technology of choice for very gross contamination or free product, but once that's been removed, then it's an appropriate way to go. And for modest to light contamination, for chopping off the tail of an asymptotic system or killing rebound, then biological systems and enhanced natural attenuation really comes to the fore. What about the matrix-related patterns? Well, these exist because some technologies only work efficiently in permeable strata, whereas some technologies can really work in any porous formation or any porous strata. Integration can therefore be beneficial because different uses of different technologies can be used to overcome matrix-based performance limitations, and each technology can still be applied where best suited. So, hence the spatial and sequential approaches can be beneficial. Well, what do I mean by matrix-related problems? What do these really look like? Well, in practical sense, they'll look something like this. This is a graph of the remediation performance of a pump and treat system that was put in about 1985, this particular one in California. What you can see in the green line here is the amount of mass that was getting removed year by year by this remedial system. What you can see in this red line here is the cost it was costing to actually remove each new unit of massive contamination. Now remember, the costs of running this piece of kit are pretty much fixed. The fuel costs are the same, the maintenance is the same. So when it's recovering a lot of mass, the return on performance is very high. But as the cleanup rate starts to reduce, the cost per kilogram of material removed starts to increase. The efficiency is actually starting to drop. The technology was wonderful to begin with, but as the concentration drops, it ceases to be so efficient. Well, why is this? Well, if we gaze deep into the matrix to see what's going on, then among the patterns of green and blue that emerge, we see something like this. This is a very interesting slide that comes out of some work in the United States by Donner and Sale. And what you can see here are two perspex sheets with effectively aquifer material in between. These are the high permeable zones. It's been flushed with a fluorescein dye. And you can see how the fluorescein has spread through the sandy matrix quite effectively. And these darker areas are clay layers. Here you can see that the fluorescein has spread its way into the low permeability zone, pretty much completely here. But in some of these bigger layers, the inside's probably clean, but the outside is still quite tinged with the contamination. What happens then when you turn on the pumps and the pump and treat system starts to kick off? You get something that looks like this. What you can see is that the sandy areas have been flushed clean immediately. So going back a few slides, that's this wonderful recovery you're seeing right here. But the contamination continues to bleed out of the low permeability zones, on and on and on. So these tails of contamination that keep coming out will carry on for a long period of time. Why is this? It's because the driving force that's pushed the contamination in has been diffusion, it's been concentration driven. And when the contamination around these layers is high, the concentration gradient forcing the contamination in is high, it goes in quite quickly. When you try and reverse that, the concentration in here is nowhere near as high as it originally was in the outside matrix. So consequently, the driving force to take it out again is not the same. The rate that it'll come out again is not the same. So therefore, the time it takes to come out again is much longer. Consequently, these tails you get will last and last and last. So typically, you'll see a good recoverable mass to begin with, but then recoverable mass will come out and out and out. You'll never quite get to the cleanup standard unless you're quite lucky. Unless you hit the system with a different approach. If you come in with a diffusive technology, an oxygen release compound, or some form of enhanced bio which will provide an ongoing source of electron donor or electron acceptor, then you can basically use diffusion as your friend to drive the remediation reagent into